Good afternoon, everyone. Welcome to Takeo Tuesday. It is December 7th, and it's the 80th anniversary of Pearl Harbor. Not that I was around, but maybe, well, anyways, quite an event. I had the opportunity to tour that museum out there or place in Pearl Harbor, and but put it on your bucket list if you ever get a chance. It's quite the place. Anyways, Brett Zerba, applications engineer with Takeo. Most of you, I've been looking at the names that are popping up here. I have been through some of these before, if not, hopefully all of them, but I kind of doubt it. Hopefully anyways, thank you for attending. We really do appreciate it. I will be moderating today's event, today's webinar. Rich Medairos will be the main presenter. So I will be monitoring questions and bringing them up with Rich as we go towards the end. Pertinent questions when they come up, I might answer some directly to you. So if you do type in a question, I may send you the answer privately. So please, watch for that. So if a couple of you can raise your hand so we know that you are seeing us and hearing us, because Rich and we always have issues. Oh boy, good. Thank you. There's Ada and others are putting their hands up. So good, Art. Thank you, Art. So good. That's a good sign. You never know with technology, especially for Rich and I don't know. We seem to have more hiccups than most. Hi, Craig. Thank you. Again, today's presentation's on expansion tanks. It's one of those subjects that pieces of equipment that sometimes gets forgotten, but it's very, very important. And Rich is going to get into that. Very, very important in systems for different reasons, for a couple of different reasons. And Rich will cover that for us. So there are no handouts today, but 24 hours after today's presentation, look for your email and you should get a copy of the recording. It is being recorded, as well as a PDH certificate if you can need it, or if you need it for yourself. Or if you want to frame it and put it, on your office wall with the 30 other ones that you have from Takeo. As you know, Takeo is a privately held company, third generation. Johnny White Jr. is currently the owner. We are headquartered in Cranston, Rhode Island, but we're a worldwide company. We have places in Switzerland. We have places in Canada. We have places in Italy. And other places. Vietnam, we have a foundry in Vietnam that does stainless steel work for us. So we are worldwide. People think of us sometimes as the little guys, but we're a lot bigger than people think. But remember this: we are the green pump guys. So, anyways, I think I've done enough of my introduction here. And please type in the questions as we go. Rich is as knowledgeable as anybody on this subject and any HVAC hydronic subject. So I guess that's about it. Rich, take it away, my friend.
Well, thanks, Brett, for that great introduction. I'm actually doing a quick test here to make sure that my pen is working properly and that it's going out to the outside world. So hopefully
looks just like me.
Does it look like somebody you know?
Yeah. I'm looking in a mirror.
Oh, good. All right. Well, we know that works. So quick intro regarding myself for those that haven't met me. My name is Rich Medairos. I'm one of the senior systems engineers here at Takeo. I am a PE registered in several states, and I've been with the company. Well, I actually passed my 9th year anniversary, Brett, a couple of weeks ago.
Awesome.
Yeah, in November. So that's kind of exciting.
Seems like only yesterday, my friend, that you and I were working on the IDC. Not that everyone knows that. Anyways.
So that's kind of cool. And I've been in the industry for several years. So we're going to talk about expansion tanks this afternoon. And I have a very quick agenda here. Why do we need expansion tanks? It's one of the primary questions that come up. Types of expansion tanks, Boyles Law, touch base on that, which is the fundamental theory behind expansion tanks, expansion tank sizing, and then we'll make a quick selection. And what does the location of the expansion tank, how does that influence the expansion tank? And as Brett mentioned a moment ago, we do encourage you to ask questions during the presentation. You can type them in. Brett will ask me to pause periodically, and we'll do our best to answer the questions. And if we have some time left over at the end, we'll certainly answer some last-minute questions. So, Brett, any questions out there?
No, nothing
Oh,
yet, my friend.
nothing. Okay. So here we have a very, very simple diagram for a hot water heating system. And as I have the title up on the top there, it says, why do we need expansion tanks? Well, I'm going to state the obvious. When you take a fluid, like today we're just going to focus our attention on water. If you think about water in a closed loop, pressurized piping system, when you increase the temperature of that water, it will expand. And if the water has no place to expand to, then the first thing might happen, and hopefully it does if it was sized properly, is that the safety relief valve, which I'm pointing to right here on the top of the boiler, that will open up and relieve the pressure in the system. But if the safety relief does not open and the water expands and it has no place to go, then it will break something. And usually in my life, it always breaks something that's expensive. It never breaks something that's inexpensive in the system. It always breaks something expensive. So why do we need expansion tanks? Well, the main reason is to allow for a place for the fluid, in this case today, water, to expand as a function of the rise in temperature. Now, it turns out that the expansion tank is also responsible for a couple of other things. It is responsible in concert with the fill valve to maintain the minimum pressure in the system. And it's also responsible for maintaining the maximum pressure in the system. And the physical location of the expansion tank determines the point of no pressure change. So if I point to the connection here where the pipe is connected from the expansion tank, and here's our expansion tank in this little example here, to the distribution piping, if you'll notice it's connected to the suction side of the pump. And that connection point is called the point of no pressure change. So a properly designed system, this winds up being the secondary pump in the system. This one over here is known as the primary pump. Generally speaking, we put the expansion tank on the secondary side of the system, on the suction side of the secondary pump. And that maintains a constant pressure. Now, as long as let's assume for a moment that the water in this case has reached its maximum operating temperature at this point, which would be 180 degrees. And as long as that temperature remains constant, then the pressure on the suction side of the pump will also remain constant. And that's because of the functionality of the expansion tank. So to repeat, expansion tank does three major things. It determines what it allows for the fluid to expand. It determines in concert with the fill valve what the minimum pressure in the system is going to be and what the maximum pressure is going to be. And then it also determines the point of no pressure change. So that's why we need expansion tanks. Okay. Any questions before I move on, Brett?
No, just a comment. I'm not sure. Hopefully, everyone was aware of all of the things the expansion tanks do, or in the system. But that's a good time to re-emphasize that. That's for sure.
Yeah, it's worth stating the obvious. So it has a very, very important function. And someone reminded me of this. I think you and I talked about this. Someone reminded me of this a few weeks ago. One of the really cool things about an expansion tank is that it does not require any electronic chips. So we're not dependent on chip manufacturers to build our expansion tanks. So they're a very, very simple device. All right. So let's talk about the types of expansion tanks. I'm just going to list them here, but don't worry about the list. We're going to go look at some photographs in a moment so we can talk about the types. So the first type is called a plain steel tank. The second type is called a bladder style tank, and we have bladder style tanks in two categories, and most manufacturers do. The first category is called a full acceptance bladder style tank, and the second one is called a partial acceptance bladder style tank. And then the final tank is called a diaphragm style tank, and they only come in one configuration, and that's called partial acceptance. So let's take a look at some photographs and see what they're all up to. So here we have a plain steel tank, and as the name implies, it's just a steel container that has no bladder physically inside. You can almost think of it as a beer can lying on its side, although it will hold much more pressure than what a beer can will. It has a couple of connections on the left side over here, which typically would be connected to a sight glass. Kind of make this little imaginary sight glass over here. And the sight glass will give us the level of water in the glass, which is also the level of water inside this plain steel tank. So the water is at the bottom of the tank by W, and air is at the top of the tank over here. And plain steel tanks will be connected to the system ultimately. That pipe continues. And then on this side, it's usually connected to a special type of valve that allows the operator to bleed the water out of the tank and allow air to enter. So it's a dual function valve. It allows water out and air in. And most of the people will connect that to a hose bib, and it'll go into a floor drain inside a mechanical room. So we'll just kind of label that floor drain, FD for floor drain. So that's a plain steel tank. Now, plain steel tanks, by their very nature, excuse me 1 second. I'm losing my voice today, Brett.
Yeah.
Now, hold on. A plain steel tank, let's see, we talked about the floor drain.
No
Well,
pressure,
whatever.
right?
Say, oh yes, the pressure, the minimum pressure is always atmospheric pressure. So because you're starting with atmospheric pressure, and when you fill the tank with water, the tank becomes fairly large. Usually in a plain steel tank as compared to a bladder style tank, the tank has to be somewhere between 2 and 3 times the size of a bladder style tank. We'll get into that in a minute. So any questions about the plain steel tank?
Yes, actually we have yes, we do. Would this be referred to as a compression tank like the old days?
Yes. Yeah, sometimes they're referred to as compression tanks. That's correct.
And this is a great question here. Well, this is in general to expansion tanks. Can the expansion tank be used as a home on my home hot water line to increase the water pressure at the shower?
Well, the answer is yes and no. When you're talking about a residential system, generally the pressure that the residential system sees is a function of if you have say a town or city water supply, the pressure coming in from the city generally is regulated by a pressure regulator. And so the challenge comes in some, especially older cities that have older piping, they don't have that much pressure in the street. And so, and the expansion tank cannot add more pressure than what's available from the pressure regulating valve. So for example, if you needed roughly, let's say you had a 2-story residential building and you needed roughly 20 pounds of pressure for your system, if you only had 15 pounds available from the town pressure system, there's nothing you can do other than add a booster pump somewhere in the system. But if you have enough pressure from your municipal system, then you can set your system accordingly with your pressure regulating valve. So again, let's say you had 50 pounds from the street and your water system in your home only required, say, 30 or 40 pounds, two-story building, that's probably pretty common, to operate the plumbing fixtures properly, and then you'd have a pressure regulating valve, usually for your hot water heating system. So hopefully that answered that question.
Yep. And then I'm not sure if it's in all codes, but wouldn't you recommend that this type of product, any of the expansion tanks, be ASME rated?
Yes, we are a TACO is a ASME, American Society of Mechanical Engineers certified manufacturing facility. So we do not manufacture any pressure vessels that are not ASME certified. So yes, we would definitely recommend ASME certified pressure vessels.
And then can you just scoot back to your drawing? We do have a question about, not your drawing, but your little design there kind of came up just as you were moving along.
Oh, okay, hold on one second. Let
Yeah.
me go back there. Okay, we're talking about the little
Yeah,
diagram, this thing?
yes. So what is the, when you look at the expansion tank, from the top of the expansion tank to the piping, there's a 0. What is that line in reference to?
Yeah, so that is the connection between the expansion tank and the main suction side of the pump, the piping. And the software that we're using is called the HSS software. I think that's what we call it, right?
Yep. Yep.
And the software puts in 0 inches, so by default. And so you would actually need to select the proper size connection between your expansion tank and your piping system. And I think the majority of our expansion tanks, don't they have like a 1.5 or 2 inch connection on it, Brett?
Yeah, I'll look it up while you're yapping.
Yeah.
Yeah.
So yeah, so that's I probably should have blanked that out, and so that's a good point. I think I'll do that next time. I should have like
Yeah.
like zipped it out here so that because it obviously can't be 0 inches. It has to be something,
Yeah.
but that's one of the default values that's in the software. So I'm glad
And,
somebody pointed that out.
and while you're talking about design, do we need a pressure relief valve in a complex system in order to prevent damage to expansion tank on the expansion piping loop? That's probably something you'll get into later, right?
Yeah, as it turns out, you do need to have safety relief valves, and they're required by code, and you have to locate them strategically in accordance with the state, what's called, yeah, national, state, and local codes.
Excellent.
Okay, let's see what we can erase here. So we went through this plain steel tank, and the next one is called a bladder style tank, and the first one we're showing you here on this cutaway drawing on the right. This is a full acceptance, full acceptance. Well, what does that mean? If you'll notice the green, we have the cutaway version, we have the green steel tank, and then we have the rubber bladder. That's this black guy right here. And then this void space between the bladder and the steel container is where the air goes, and inside the bladder is where the water goes. And up here at the top, that's where the connection is made to the piping system. And I believe, well, Brett's going to look it up in a minute.
Yeah, the majority, as you stated, the majority of them, you know, when I just went to our website, is 1.5 inch connection.
Yeah.
Some of the smaller ones are 1 inch, some of the bigger ones are 2 and/or 3. But yeah, so
yeah, the majority of them are 1.5 inch connections. And the reason we call it full acceptance is, let's assume for a moment that the steel container in this case is 200 gallons. 200 gallons. I'm just going to put a G today for gallons. If the bladder can expand to the full volume of the steel container, which means it could also hold 200 gallons of water, then that means that it's full acceptance. Whenever the bladder capacity is equal to the steel container capacity, we call that a full acceptance tank. So I've made a little connection up here, 1.5 inch. That's for the piping system connection. Underneath this little collar right here is where the Schrader valve is, and that Schrader valve looks just like the Schrader valve that's on your car. The bottom of the Schrader valve, this one is actually a car tire Schrader valve picture. The bottom of the Schrader valve that we use actually is a threaded connection so that it bolts into the steel opening that's up here. So we have the outside steel container. We have the connection right here at the top where the pipe goes. We have the bladder that holds the water, and the space between the bladder and the steel container is where the air goes, and that's where you pre-charge the tank. We're going to get involved. We're going to get into that discussion in a moment. But you add air for the air side through the Schrader valve, which again is located in this little protective collar right here. Well, maybe this one up here is a little better. You can see it up here a little better. And so those are the major components of the bladder style full acceptance expansion tank. The next picture we're going to show you is for a partial acceptance tank. And the only major difference between this one and the previous tank is that the bladder can only hold a portion of the volume of the steel container. Again, here's the steel container that I'm pointing to. And let's assume that the steel container happens to be 200 gallons. The bladder, and I don't know what the exact capacity of the bladder might be, so the steel container might be 200 gallons. The bladder, for example, maybe is 50 gallons. I don't know until I look it up on one of our charts. But let's assume it's 50 gallons, and that's the maximum that bladder can accept. And because the acceptance volume is less than the steel container volume, 50 gallons, I'll put a little G over here, compared to the steel container of 200 gallons, that's where we get the name partial acceptance. And air, again, is here. I'll put a big letter A for the air. Inside the bladder is where the water goes, and then the air can be charged through the Schrader valve that's protected by this collar on the top. So the partial acceptance is very similar to the full acceptance, except that the bladder is physically smaller. All right. And then the last category is called a diaphragm style tank. And in this case, we don't actually have a bladder, or well, we don't have a balloon shaped bladder. We have more of a bowl shaped bladder, which we call a diaphragm. And in this case, oh, I should probably, let me go back and mention this. Let's go back here. In this partial acceptance and full acceptance, the bladder is serviceable, which means you can physically take it out and replace it with a new one. When it comes to a diaphragm style tank, the diaphragm, again, is this kind of bowl-shaped rubberized device. And that's called the diaphragm. It's connected to the inside, permanently connected to the inside of the steel container, and it cannot be serviced. So if the partial acceptance diaphragm style tank, if the bladder or the diaphragm should fail, then you have to replace the tank. You can't service it. You can't replace the diaphragm. So, and it's partial acceptance. It'll only hold a portion of the steel container, similar to the one I described a moment ago. If the steel container was 200 gallons and the diaphragm could only hold, again, this is the air side here. This is the water side down here. You could potentially rupture the diaphragm. So those are the major components of the diaphragm style partial acceptance tank. So before I go on to the next piece of the discussion, Brett, any questions?
Yep. You should be expecting this question. When should a partial acceptance be used in lieu of a full acceptance?
Well, I recommend
That's the $64,000 question, right?
Yeah, I recommend the full acceptance bladder style tanks for all applications. However, we're in a competitive market, and the reason we offer the partial acceptance tanks is because they're less expensive. And in a competitive environment, sometimes people want to be more competitive, and so we provide the same product that our competition provides. And the least expensive is the diaphragm style, which cannot be serviced, and that one is disposable at the end of its life. So we recommend the full acceptance, but we certainly understand that if money is an issue, someone may decide to put in a lesser expensive tank. They all do exactly the same job, by the way. If they're properly sized and installed properly, and we're going to get into that in a minute, they work fine. You run the risk in a partial acceptance of either destroying the diaphragm or destroying the bladder if you should try to put more fluid in there than what the design is capable of handling. Hopefully that helps answer that question.
Yeah, well, we got some great questions today. It's very interactive here. How do
Oh,
you know
good.
when an expansion tank bladder fails? Another $64,000 question.
Well, yeah. So why do bladders fail? Well, the majority of reasons for the bladder failure is that usually in a full acceptance, the amount of bladders that fail is very, very small. So let's go to a partial acceptance. If for some reason, let's assume that the Schrader valve we talked about a moment ago, Schrader valve is located up here. If someone should take the stem out of the Schrader valve and allow the air to escape, then if the system is pressurized, for example, let's just pick a number, say it's pressurized to 50 pounds, that 50 pounds of pressure will be opposed by 0 pounds of gauge pressure. It's basically atmospheric pressure. And so there's nothing to restrict the expansion of the bladder. So it could expand beyond its design capacity. Let's assume it had 50 gallons and the steel container is 200 gallons. If someone should take the Schrader valve stem out and allow the air to escape, then the bladder would eventually rupture if it fills up. And if it does rupture, this whole container inside here will fill up with water. And let's assume that the Schrader valve, someone did not remove the stem, but they inadvertently allowed the air to escape. Maybe they thought they were supposed to have 0 pounds of gauge pressure. And if they allowed the air to escape, then the bladder would rupture and the tank would fill up with water. And then if you depress the Schrader valve, water would come out. And that's how you know that the bladder has failed. Cool, huh?
Excellent. And I think I'm going to add, someone's asking about what happens when you put it on the discharge of the pump instead of on the closed loop system. But I think we should cover that when you get to the sizing. What do you think?
Yeah, let's if we have let's hold that question
Yep.
off to the side, Brett, and if
Yep.
don't answer it during the presentation, we'll answer it at the end. Okay, so let's touch base on Boyles Law. Boyles Law was published by Robert Boyle back in 1662. And here's a trivia question for you guys that are out there in the audience. What year did the Pilgrims sail in the Mayflower from England to what ultimately wound up being Massachusetts? Does anybody know what year they did that? While you're thinking about that, I'm just basically going to talk a little bit about Boyle's Law. States that the pressure of an ideal gas is indirectly proportional to its volume at constant temperature, and this famous equation is what Boyle came up with. And he said, in a closed container, the pressure and volume of an ideal gas at one point in the container is equal to the pressure and volume at another point. In other words, the pressure times the volume is a constant. And the pressure is always measured in pounds per square inch absolute. So I'm actually going to go to my whiteboard here.
1620 or 1492. Those are our statements.
Well, I'm going to give you a hint. It's definitely not 1492. 1492 is when Columbus, that's the date that was assigned to Columbus when he ran into one of the islands in the Caribbean. But yes, someone did come up with the correct answer. The Pilgrims came over here in 1620, which is only roughly 40 years, about 45 years, 46 years prior to Robert Boyle publishing his law. So that was about 360 years ago. Because last year we celebrated the 400th year anniversary of the Pilgrims landing in Plymouth. Since I happen to live in the next town away from Plymouth, it was a big deal. Okay, so let's look at a container for a moment. Let's this is the before container, and so I'm just going to put in a B here for before, and then over here I'll put an A in for after. Well, maybe I should spell that out here, AFTER. Now remember, we're talking about Boyles Law has to do with the ideal gas. So let's assume our container, check my spelling, Brett, because sometimes, as you know, I tend to screw up my spelling. Did I spell that correctly?
With the E, yes.
Yeah. So here we have a steel container that's 200 gallons. I'm going to put 200 gallons. And initially, this steel container is filled with air. So I'm going to put air in here, A-I-R. And let's assume that the pressure, if I had a pressure gauge, stick a pressure gauge over here. Let's say the pressure inside my steel container happened to be 50 pounds. 50. P-S-I-G.
Spelled that right. You
How's
are.
that? Pretty
Good
good.
spelling.
So it's a 200-gallon container, and it's 50 pounds of pressure. So what Boyle said was that if I take that same container and I compress the air, so now I'm going to take that same exact container, but the only difference is that I'm going to allow water to enter the bottom of the container. Let's say I've got a pipe over here, and my water level increases over here. So I'm going to put a W for water down here and an A for air up here. All right. And let's assume that I let in 100 gallons of water. 100 gallons. The question is, can anybody tell me what the pressure of the air is over here?
What was that formula? Remember the formula.
So basically, what Boyle said was the pressure, let's do it inside the tank here. He said that the pressure times the volume over here is going to be equal to, and I'm only talking about the air now, the pressure P2 times the volume over here. And if you recall, we said that the pressure has to be measured in absolute pressure. So those two are equal to each other. So if we simply rewrite his equation, then we can solve his equation for P2.
We got a lot of hundreds popping up.
Well, in a moment, I'm going to show you that that's not correct. P2 is going to be equal to the initial pressure times the ratio of the air volumes. So the volume over here, what was the air volume over here? I think we said that was 200 gallons.
Yep.
And then if I allow water to enter, allow 100 gallons to, how much air am I going to have for V2? Well, it's going to be 100 gallons, right?
Yep.
But remember, we said that the pressure for Boyles Law has to be converted into absolute pressure. So someone had close to the right answer. So we first have to take 50 plus 14.7, assuming that we're at sea level for a moment, then that would be 64.7. That would be the absolute pressure, P1 absolute pressure. So P1 would be equal to 64.7 pounds per square inch absolute, PSIA. So that's the pressure that we would double up here in this equation. So 200 divided by 100 is 2. So 2 times 64.7. I've got my calculator out, Brett, so I don't mess this up. 64.7 times 2 is going to be 129. So P2 is going to be equal to 129.4 pounds per square inch absolute.
We had someone said about 130 PSI.
PSIA, and then to get it back to gauge pressure, we simply subtract 14.7 minus 14.7. That comes out to 114.7. So the pressure over here is going to be 114.7. And it's important that you recognize that it's the absolute pressure, PSIG, PS, there's a PS. Wow, squeeze that in there, IG. So any questions about Boyles Law?
Nope.
All right, now for a quick question to make sure everybody's on the same page. What if I had exactly the same case, only instead of starting with a 200-gallon tank, I started with a 400-gallon tank? Would the final pressure be greater or less? Anybody want to take a quick guess?
They're all afraid now.
They're all afraid, yep. So if I started with a 400-gallon container and I only allowed 100 gallons of water to enter, then the air would go from 400 gallons down to 300 gallons, and my ratio would be 4/3, which means it would be 1 1/3 times the pressure. So the pressure would be less. The larger the expansion tank for a fixed amount of expansion, the final pressure is less. So if you're trying to decide whether you want more or less pressure in the system for a given amount of expansion, if you make the larger the tank you make, the final pressure is lower. The smaller the expansion tank you make, the final pressure is larger. And that was basically what we wanted to tell people about. Okay. So now let's get into sizing. Any questions before I go into the sizing?
Nope.
So when we size an expansion tank, there are 6 things we need to know. We need to know what the minimum or fill pressure is. We need to know what the maximum pressure of the system is, the minimum temperature, maximum temperature, the fluid type, which is very important, and then the system volume. So how do we figure out each one of these? Well, let's figure out the first one on the list. That's the minimum or fill pressure. That probably takes the greatest amount of time to figure out. So let's look at a very simple example. We'll have given a 75-foot tall office building. Let's find the expansion tank size. So we want to know what the minimum pressure is. So here I have a 5-story office building that's 75 feet tall, and our mechanical room is at the lowest level. So we're going to assume that our expansion tank is in this part of the building. And we're going to kind of stretch our imagination and assume the piping goes from the floor of the mechanical room. We know in the real world it probably doesn't, all the way up to the roof of the building. And the height of that column of fluid turns out to be 75 feet. So if I fill this pipe with water, and let's assume that I turn the water down, the pipe rather down here, and I get my bucket from Home Depot. I like the Home Depot buckets this week. Got a little valve here.
Orange. They're orange.
Yeah, they're orange. And I just let a few drops of water come out of that, and that. Now I know the pipe is filled, and then I'm going to shut off the fill valve down here. Can anybody tell me what the pressure is going to be at the top of this piping system? If I put a pressure gauge up here, what is that going to read in pounds per square inch gauge? I'm also going to ask you in a moment, what is the pressure going to read down here at the bottom of our column of water in pounds per square inch gauge? Did anybody type in the pressure at the top, Brett?
A lot of zeros.
That's correct. It would be 0 pounds per square inch, PSIG, at the top of this piping system. Does anybody can tell me what the pressure is at the bottom of the piping system? So it's 0 up here.
I see 32.4.
I'm going to round that off and say the pressure down here is 32.5. In a moment, I'm going to tell you how I'm going to show you the calculation, but I'll tell you what it is. And that is simply the height of the column of fluid divided by 2.31, because the conversion is 2.31 feet per PSI, feet, per 1 PSI. So I'll just put a 1 in there, PSI. So all we have to do is divide the height of the building by 2.31, and we get the pressure at the bottom. Now, we do not want 0 pounds at the top of the building. We want something greater than that. And the reason we want a pressure greater than 0 pounds is for a couple of reasons. We want to make sure we have enough pressure to push any air out at the top of the piping system through the air vents. And we also want to make sure we have enough pressure so that the pump, if there is a pump at the top or a valve, that they don't cavitate. And so most engineers will pick a pressure at the top of the building of somewhere between 5 to 10 pounds. And for today's example, I'm going to use simple math. I'm going to pick a value halfway between those two and make it 7.5 pounds. So if I add enough pressure from my fill valve that's inside the mechanical room to get 7.5 pounds at the top of the building, what's the new pressure going to be at the bottom of the building? Well, it's 7.5 plus 32.5, so that pressure at the bottom of the building is going to be 40 pounds. Any questions about that, Brett?
Nope. Ed wrote 40.
Excellent. So now we're going to go back to our little diagram over here. Well, actually, we're going to skip. Say the minimum pressure is the height of the building converted into pounds per square inch gauge. And we get that by taking the height divided by 2.31, which is 32.5 pounds. We want to add somewhere between 5 to 10 pounds for pressure at the highest point. We're going to use 7.5 pounds. We add that 7.5 to the 32.5, then the minimum pressure is going to be 40 pounds. So I'm going to pause here for a moment in case anybody wants to take a screenshot or a picture, because this is how you figure out what the minimum pressure needs to be at your expansion tank and at the fill valve. So while folks are doing that, I'm going to move on to the next piece of the puzzle. Okay, I want to assume everybody had enough time to take a picture or do a screenshot. So now we've figured out what the minimum pressure happens to be, and it turns out it's also known as the precharge pressure. So when we ship an expansion tank from the factory, that expansion tank on the air side of the expansion tank is precharged to 12 pounds. And then we ship it over the road and deliver it to the site. And assuming for a moment that the tank is at the same temperature in the mechanical room before it's installed into the piping system as it was when it left the factory, then that pressure should be the same, should be 12 pounds. But in our example, the air side of the system needs to be precharged to 40 pounds because that needs to be the minimum pressure. And we have to precharge the expansion tank before we connect it to the piping system. And the precharge pressure and the fill valve pressure is all the same. 40 pounds for the fill valve, 40 pounds for the precharge in the air side of the tank. Precharge the tank before you connect it to the system, because remember, when it comes from the factory, it only has 12 pounds of pressure. By the way, you should always check the pressure in the expansion tank before you install it into the system and before you precharge it, to make sure there are no leaks, because if it leaves the factory at 12 pounds, it should arrive at its destination at 12 pounds, assuming the temperature is the same. If it's not, if it's dramatically less than 12 pounds, then you probably have a leak, and you should test the tank for leaks before you put it into the system. So any questions about the minimum pressure?
Nope.
Good. So what's the maximum pressure? That's the next thing we need to figure out. Well, this is one method that you can use. There are multiple methods. They all are based on the same fundamental philosophy. And that is to say that we have at the lowest part of the building, remember we said our mechanical room is the lowest part of the building. And we have down here at the same elevation as the expansion tank, we have some type of piece of equipment that has a maximum design pressure of 150 pounds per square inch gauge. If that's 150 pounds, we don't want the piping system that's delivering pressure to that device to ever get to 150. So we're going to size the relief valve, or rather set the relief valve, safety relief valve, at roughly 10% below that value. So that means we're going to set the relief valve at 135 pounds. Let's go back here. We're going to set the relief valve at 135 pounds. So that's going to be the pressure at the discharge side of the pump. Actually, it's going to be, we want the pressure at the discharge side of the pump to be a little bit less than the safety relief valve setting, because if you're close to the safety relief valve setting, that relief valve can leak or drip, becomes a nuisance. So we want the pressure on the discharge side of the pump never to get above 130 pounds, because if that's never above 130, then we're not going to get to 135, which protects the equipment. If the pump has a pressure differential across it of 20 pounds, then the maximum pressure we want on the suction side of the pump is 130 minus 20, or 110. So the maximum pressure that we want at the suction side of the pump, which also happens to be the maximum pressure we want at the expansion tank, is 110 pounds. So now we know what the maximum pressure is at an expansion tank and the minimum or fill pressure at the expansion tank. And those are the two most critical, well, all the values are critical, I shouldn't say that, but those are the two most complex values to obtain. Any question about that, Brett?
Nope.
Okay. So now we know what the minimum pressure is, we know what the maximum pressure is. The rest of the values are pretty straightforward. The minimum temperature, sometimes referred to as the fill temperature, depends on the water temperature that you have in your building. And to be conservative, if you happen to be in the Northeast, like in New England, we know that the groundwater temperature is about 50 degrees Fahrenheit. So that's about the lowest temperature that you would have for your fill temperature. In our case, our simple example, we said it was a hot water heating system, and the maximum temperature was set at 180 degrees. So now we know what the maximum temperature is. The fluid type we're saying is water in this case, and that the system volume, well, the system volume is a tedious calculation if you try to do it manually. It's the volume of the water for the entire system, which includes the volume of the water in the piping, the equipment, the valves, anything that has water in it. And if you're using the HSS software, if you put the pipe lengths in relatively accurately, it will calculate the system volume for you. So you either do it manually, which is very tedious, or you can use software, which is very simple and fast. So now we have the 6 major things that we need to size an expansion tank. So I'm going to go live to our website. A little luck here. I'm going to go to our website over here. And I'm at our home page, and I'm going to go to Selection Tools. Click on that, and then on the left-hand side it says Expansion Tanks. And I'm going to zoom in. Let's see if I can zoom in here. And I'm going to fill in the values for our this is our Taco's Expansion Tank app. So the units we're going to leave at US units. The fluid we said was water. I'm going to initially leave the pipe material at copper. The system volume, I believe we said, Brett, was 2,000 gallons. The minimum or initial fill or operating temperature was 50 degrees Fahrenheit. The maximum is 180. The fill pressure, which is the minimum pressure at the expansion tank, is 40 pounds. The maximum pressure we said was 110. And then we're going to use a standard selection here for now. I'm going to click on search. Before I look at the search results, I'm just going to scroll down here a little bit to point out that the software has calculated, well, actually the first thing it did, whoops, what happened to my pen? The first thing it did was looked up the specific volume of the fluid at the minimum temperature and the specific volume of the fluid at the maximum temperature. Those two values in concert with the total system volume allows us to calculate the expansion. In this case, it's roughly, I'm going to round this down in a moment, you'll see why. I'm just going to call it 53 gallons. That's the water that would expand as a function of temperature. In other words, all we have is 2,000 gallons, whether you have it in a piping system or if you have it in a 2,000 gallon bucket, and you heat that water up from 50 degrees Fahrenheit up to 180 degrees, it will expand an additional 53 gallons. Isn't that cool? We're going to ignore the plain steel tank one for a moment, and we're going to say a bladder style tank requires a steel container volume of 95.2 gallons as a minimum, and the acceptance volume needs to be at least 53 gallons. So we're going to go over here on the right. I'm going to look at those selections the computer has made. So we'll notice that the first one is called the CA450-125. The CA is the tank configuration model. The 450 is the size in liters. And if you do a conversion, you'll find that 450 liters is 119 gallons. This other value over here, 125, that's the pressure rating of this specific tank. You can get them in other pressure ratings. If you look on our installation instructions or submittal data sheet, I think it's on. It shows you the variety of different pressures that you can choose. But for today's example, we're going to leave it at 125 pounds. The tank steel container volume is 119. That's greater than what we had down here, which we said was 95. And the acceptance volume, that means that the amount of fluid that the bladder can hold happens to be equal to the tank volume. Whenever the acceptance volume is equal to the tank volume, then that's a full acceptance tank. So that first tank selection will do the job. Second one will also do the job. It has a minimum volume of 112 gallons for the steel container. We need at least 95 gallons. It has an acceptance volume of 61 gallons. And now, if you'll notice, the acceptance volume is less than the tank volume. So therefore, it's called a partial acceptance tank. But 61 gallons is greater than the 53 that we need, and so that would do the job. We can say, yes, that's obviously. Hopefully the software has not made a mistake. And then the last one I want to point out is this guy right here. The tank has a steel volume of 57 gallons. Well, we needed at least 95, so we're going to multiply that by 2. We're going to have 2 tanks. 2 times 57 is 114. So we meet the requirements of 95 gallons. And the acceptance volume is 27, and since that's less than the steel container, then we say it's a partial acceptance, but you multiply that by 2. 27 times 2 is 54. If you recall, we said we needed approximately 53 gallons worth of acceptance or expansion. So that's pretty much everything I wanted to show you initially. Any questions?
Yeah, let's go over a couple of the questions. So the last one you just circled, 2757. I guess it can be a general statement that if the acceptance volume on this chart is less than the tank volume, then that's a partial acceptance tank model, I guess.
Correct. That's
Yeah.
absolutely correct.
Right. And then when you were doing your calculations, at one point, how did you decide the pump delta T? Pressure drop in the system? Jonathan's asking.
Well, in this particular example, I'm assuming, let me go back to that. Can I go back to that? Yes, I can. Let me go back here. Where are we here? I think this is it. Yep. Okay, so in this case, if you'll notice, I said the maximum pressure that this pump could produce is 20 psi at shutoff head. So in other words, let's assume for a moment that someone screwed up and they put a isolation valve on the pipe over here and they close that valve. And then they put another isolation valve over here and they close that valve. That means that there's zero flow through the pump, and that's called a shutoff head. So that means the maximum pressure that this pump could possibly produce is at the shutoff head. And if that's the case, it just happens that I picked the pump that had a differential pressure at zero flow or at the shutoff head of 20 psi. That's where I came up with that number. The actual pressure differential that the pump can produce at shutoff is the one that you should use in your calculation. Does that help answer that question, Brett?
Yep. That perfect. And then here's an interesting question. If the chillers are on the roof and the expansion tank and pumps are a level below, how does that affect maximum pressure?
Well, the calculation is still exactly the same. And you take the height of the column of fluid above the connection of the expansion tank. So in this case, let's assume that the chiller is in the penthouse and the pump is one level below. And let's just arbitrarily say that the floor-to-floor height happens to be 20 feet. So the piping height from the center line of the, at the expansion tank connection to the highest pipe in the system might be the floor-to-floor height, which is 20 feet plus whatever the height is of the equipment on the upper floor. Maybe that's 10 feet. So the height differential would be 30 feet. And you would want to make sure that you had, so you use the same formula, only this case it's only 30 feet. So you take 30 divided by 2.31, which is about 12.9, we'll call it 13 pounds, plus you add somewhere between 5 and 10. Let's say you added 10 pounds. That means the pressure at the expansion tank wants to be 23 pounds.
Just because it's a little lower.
Yep.
And someone's asking, and this gentleman's last name is Schrader, believe it or not.
Hey, maybe he's related to August
I
Schrader.
know, he might be able to buy us a drink.
Yeah, I know.
Can you bring up the minimum fill pressure slide again? Something else popped up on the screen when I took a screenshot. So,
Yep, let me see if I can go back there. Let me erase this for a moment. And we want to go back to where we said it would be. This slide here, the minimum fill pressure and the pre-charge, yes. What's the question?
Nope, he just wanted to take a picture of it. Something probably popped up on his computer.
Yes. So let me, maybe I didn't mention this, maybe I glossed over it too quickly, Brett, but when we ship the tank, we ship it from the factory pre-charged to 12 pounds on the air side. And it's important that you do the calculation to determine what the minimum or fill pressure should be. And now you should pre-charge the air side of the tank before you connect it to the system. In our example, to 40 pounds. You have to take compressed air from compressor, go over to the Schrader valve, just like you would fill up a car tire, and you would pump that pressure up to 40 pounds. Test it a couple of times, and now you can connect it to the system, and it'll reach equilibrium fairly quickly because the fill valve is trying to maintain 40 pounds. The tank has got 40 pounds, and so there's a match. Okay, next question.
Can you oversize an expansion tank? I'm sure undersizing is not good, but what about oversizing?
Well, if you remember the little diagram that we put together for Boyles Law, we said that if you made the tank physically larger, then the maximum pressure winds up being less. So in our example, the maximum pressure at the expansion tank was 110 pounds, and that was based on a tank volume of roughly somewhere between 95 and 100 gallons. That's what the software said. Let's just go back to that to make sure we're talking apples and bananas. So we said that the steel container needed to be roughly 95 gallons, and the expansion volume was 53. Now, if I arbitrarily made that tank, say, 200 gallons, just arbitrarily make it 200 gallons, we said that the maximum pressure would be less. It would never reach 110 pounds if everything was sized properly. It would be less than 110 pounds. So there's no penalty to the system if you should oversize the expansion tank other than cost and real estate. But you can put as big an expansion tank as you want in that system, unless you had some reason for maintaining a higher maximum pressure.
Can you go back to your PowerPoint? I think Mr. Schrader wanted us to go back another slide.
Yes.
Let's see. He said there's a one calculating the minimum pressure. Can you go backwards?
Yeah, hold on 1 second.
Yeah. The bat phone's on.
Sorry about that interruption, Brett.
All right. Okay.
They wanted to see another slide?
Yeah, go back. Maybe there's one. It says you had a slide calculating the minimum pressure. Well,
yes.
I guess.
Let's see. I think it's over. Yeah,
here it is. One there. Bingo.
Yep.
And then while people are taking a picture looking at this, so let's try to cover that statement. And this is from one of our reps, so I really do think it's probably pertinent. Maybe what happens when you install the expansion tank on the discharge side of the pump in a closed system?
Let's go back to our little system diagram that we started with way back in the beginning here. Okay.
Bingo, bango, bongo.
Okay, so the expansion tank, if it's connected to the suction side of the pump, it's going to maintain. So if, let's assume that you have not started the boiler, you simply filled the piping system with the fill temperature of 50 degrees Fahrenheit, and you've got the minimum fill valve at 40 pounds, you've got the expansion tank at 40 pounds, the suction pressure on the pump is now 40 pounds. So far, so good?
Yeah.
Okay. If it's a variable flow, which in this case it would be because we have two-way valves on the terminal devices, if it's variable flow, the suction pressure remains constant, but the discharge pressure goes up or down as a function of the speed of the pump and the position of the two-way valves. But the suction pressure remains constant. And in order to maintain the proper operation of the pump, especially as it pertains to net positive suction head, we want to maintain a constant minimum pressure at the suction side of the pump. If I put the expansion tank on the discharge side of the pump, guess what's going to happen? The discharge pressure is going to remain constant, and now the suction pressure is going to vary. If the suction pressure varies as a function of the speed of the pump, the faster the pump runs, the lower the suction pressure is going to be, and you run the risk of the pump cavitating because the suction pressure is too low relative to the temperature and the pressure of the system. Hopefully that helped answer that question.
Yep, you're all caught up.
Well, we're just about at our ending point, Brett. We're hitting 1 p.m. Do we have a last question that we want to answer, or it's your call?
Nope, I think we're all set.
Well, in that case, I'm going to take this just one quick moment here to thank everyone for participating in today's TACO Tuesday. Hopefully you got something out of it. And in a second, I'm going to turn it over to Brett. Hopefully you folks will have a great holiday if we don't see you. Are we going to see folks again, Brett? Not for TACO Tuesday, right? Before the holiday?
I think we have one more.
Do we have one more?
Yeah, you know what? We have one of your favorites, manual pressure drop calculations in 2 weeks.
I like that one. Yeah.
Yeah.
When is that scheduled for?
2 weeks from today.
2 weeks.
Christmas Day.
If
Christmas
someone
Day.
decides they don't want to participate in the next presentation, have a happy holiday to everyone, and hopefully,
Kimberly,
folks.
thank you very much. She answered all the questions, and she did a great job. So, and she's saying this was really good. So I wanted to make sure I shouted out to her.
Oh, good.
And
all right. So at this point, Brett, I'm turning it over to you. You can sign off whenever you want.
Thanks, Rich. Great job as usual. As I said at the beginning, and I think some of you are finding out the more and more you listen to him, he is very, very knowledgeable, and his mathematics, many of us have had math courses throughout our lives, if not all of us, and Rich presents it in ways where it's understandable, even for old people like myself. So anyways, thank you for your time. Hopefully we'll see you in 2 weeks. And signing off. Look for the email tomorrow. The recording will be available. Take care, everybody. Bye.